Hey kiddos, today we're going to take functions and write them as power series, and it's kind of the coolest thing that we do with power series. It's kind of the whole point of power series. So let's get started. This is your most basic, most generic power series. I know it's a power series because I've got x's included now, and as I start to list terms, I can see I make polynomials. So one term is not exciting, but two terms is a line, three terms makes it quadratic, etc., etc. So I hope you notice that this power series is geometric. And it's geometric with r equaling x. So we're multiplying by x to move from term to term to term all the way along. And then I hope you remember from last week that we can find the sum of this series using a geometric sum of a over 1 minus r. So for this power series, it would be equal to a, which is the first term, which is 1, over 1 minus r, which is x. All right, so we're just writing it, but let me tell you, like what you just did was so cool. This is a function. This is an f of x equals 1 over 1 minus x. It's a rational function. If Pickle asked you to graph it last year, you probably could have gotten there eventually, but you know what that looks like. So what you've just done is taken this rational function and you have written it as a polynomial. And that's really cool. So our goal today is to take functions and write them as polynomials. So functions that are not polynomials and write them as polynomials. We can do it with anything. Not today. Eventually we can do it with anything. But that's what we're doing. So the other thing that's going to happen to you over the next couple days is I'm going to show you 6 very common, widely used functions that are written as power series, and I need them to go into your memory. So this is actually the first one. This needs to go into your memory bank. You need to be able to give me, if I give you this function, you need to be able to write it as a power series and write it as a summation. And then all the other ways around. So if I give you the power series, you should be able to write the function and the summation. So you've got to know all 3 pieces for this one. All right, so that's your most basic one. Here's what we're going to do today. We are going to take different power series or different functions and write them as power series. So like this one. That is a rational function again. We're going to write it as a power series. So I hope you see that it looks kind of like an a over 1 minus r, because this one is also geometric. I'm just sticking with geometric for our first example, but of course they won't always be. It's not completely a geometric form because of this 4. So we're gonna rearrange it first. We're gonna rearrange it by factoring out a 4 in the denominator. So this is x over 4. And then I don't like that down there. I want to think about this as 3/4 over 1 minus x over 4. I like the way that looks better. It's going to be easier to work with. So remembering a over 1 minus r, if I can pull pieces from this, I can write a power series. So a is 3/4 and r is x fourths, x over 4. So we are going to try to write the terms of the power series using that information. So this rational function that you were given in the beginning is now approximately equal to this geometric series. Now, geometric series starts at 3/4 because that's a, and then it gets multiplied by x over 4 as we move between terms. So plus, if I multiply by x over 4, I'm going to get 3x over 4 squared. If I multiply by x over 4, I'm going to get 3x squared over 4 cubed. If I multiply again, I'll get 3x cubed over 4 fourths, etc., etc. We did it. You just wrote a rational geometric function as a, well, you just wrote a rational function as a geometric power series. And that was great, and it wasn't too hard. You had to do some algebra manipulation on the front end. But again, this is only, I can only do this if it's geometric, and I can go find this sum formula and break it down that way. And of course, They will not always be geometric. So I want to show you another way. We're going to do the exact same question another way. So this way we did it by knowing that it was a geometric manipulation. And this way we're going to do it using function notation. And to be very honest, this one happens a whole lot more. So I know the geometric was quick. This one's quick too, but it happens a whole lot more. So don't learn one way and never listen to me again. We are going to use the fact that we have this function in our memories. And maybe it's not there yet, but it needs to be there eventually. So if this function is in your memory, equals 1 over 1 minus x. We're going to use that function that I know and turn it into the function I am trying to make. So if you remember, oh, it's right there. The function we are trying to make is 3 over 4 minus x. And I'll go ahead and you'll have to do the algebra on the front end anyway. So it's 3/4 over 1 minus x over 4. So we're going to use what we know and trying to turn it into what we're going to make. First thing we're going to do is turn our x, replace our x's with x over 4s. So in function notation, that looks like f of x over 4. Because I'm going to take all my x's and write x over 4s instead. And we're going to baby step this one because it's the first one. So 1 is still 1. X over 4 is now x over 4. Or I'm sorry, x is now x over 4. X squared is now x over 4 squared. And x over 4 cubed. And that's enough for me. And that now equals 1 over 1 minus x over 4. So we're almost there. The last thing left to do is to get this 3/4. Remember, this 3/4 is just sitting up top. It's just getting multiplied. So the function notation way of dealing with that is just to multiply my function by 3/4. So I still have, well, I had 1, but now it gets multiplied by 3/4. Plus 3/4 times x over 4. So I'm distributing it into the polynomial. I have to multiply every term by 3/4. Plus 3/4 times x over 4 squared, etc. I'll do one more. And then when I write my final, I multiply it by 3/4 as well. And now I have here what I was trying to make, so I'm done. It absolutely can be cleaned up. You need to notice that these two things are identical once they are cleaned up just a little bit. It doesn't even take very much cleaning. If this were a multiple choice question, they would clean, so be prepared to see these written a couple different ways. All right, we're going to do 2 more that are not geometric. So now I would like for us together to try to create a power series function. Let me write it as h because we've already used f. For natural log absolute value of 1 plus x. Oops. We're going to do this one with function notation manipulation like we just practiced. And that means we have to start with this function that is in our memories. And if it's not there now, it's going to be eventually 1 over 1 minus x. So I need a way to turn this function into this function. And then I can write the terms for it as I go. So the first thing I'm going to try to do is turn this minus x into a plus x. And the way I do that is by taking my function f from up there and replacing all my x's with negative x's. So let's see what that does. So now this is 1. Instead of x, it's minus x. Then I have plus negative x squared is positive x squared. Negative x cubed is negative x cubed. So it created an alternator. It's now making my series an alternating series. So this equals, I should put approximate equals, 1 over 1 plus x. So we're getting closer. I have the 1 plus x like I need. Now, how in the world am I going to put a natural log in there? Well, you can do anything you want as long as you do it everywhere. And I know that if I take the integral of this function, I'm going to get the natural log of 1 plus x. So that means I have to go through this polynomial and integrate every term. And I know that sounds like a lot, but remember it's a polynomial. And that's the beauty of this, is now I'm integrating polynomials, which means I'm just adding 1, dividing by the new, adding 1, dividing by the new. So I'm going to put my symbol here too, just to show I'm doing it everywhere. And I think I'm done. I think I'm going to have my final answer. So h of x equals, if I integrate 1, I get x minus x squared over 2 plus x cubed over 3, etc. And that is equal to the natural log of the absolute value of 1 plus x. I'm going to write it in summation notation too as well. So this is going to be the sum from nothing until forever. And I need an alternator. So I'm going to do -1 to the n to alternate it. My x is being raised to a power that is 1 more than where I started. And the denominator is the same as the power. That's how I figure these. This is the next one that needs to go into your memory bank. I told you there were going to be 6. We're actually doing 3 of the 6 today. So that one needs to go into your memory. All right, last one. The last one that needs to go into your memory for today is a power series expansion for, let me use a different letter, J, inverse tangent. Okay, again, we are only going to pull from this one and only series today. I know you now have 2 in your memory, but we got the second one from this one, so we're not going to go backwards. 1 over 1 minus x. All right, I need to turn 1 over 1 minus x into inverse tangent. Okay, if we were in class, we would all sit and twiddle our thumbs at each other and yell like ideas back and forth, and I'd make fun of you and be great. But since we can't do that, I just have to tell you, and that takes some of the fun, some of the joy away from me, but we're going to do it anyway. My goal, just so you know where I'm headed, is I want to turn this, I want to take 1 over 1 minus x and first turn it into 1 over 1 plus x squared, and then I can integrate it and turn it into inverse tangent. So this is still going to be a 2-step process, but I'm trying to get here so that I can take an integral and get inverse tan. So we're going to start it the same way we started our natural log almost, is we need to replace all of our x's with negative x squareds. So everywhere there's an x, we're going to put a negative x squared instead. So 1 is still 1 minus x squared. Now x squared, negative x squared squared is going to be a positive x to the 4th. And then I have a negative x to the 6th, etc. And this one is alternating. Throwing a negative in is always going to make you an alternator. But it's only got even powers right now because I have an x squared in there. So I should do it here too. 1 over 1 plus x squared. So now we go and we integrate every term to get our inverse tangent. And throw integral, integral, integral. So this is going to be j inverse tan. All right, each term. If I integrate 1, I get x. If I integrate x squared, I get x cubed over 3, x fifth over 5, x 7 over 7. And then this is why I'd put inverse tan. I'll put it over here just so it's consistent with the other ones, the way I wrote the other ones. Then if I go and make a summation for this, I'm going to start at 0 and go forever. I need an alternator again. I'll start it at n. And then I need only odds. So I need x's raised to odd powers and odd denominators. And the way you make odds is you double and add 1 or double and subtract 1. It just depends on where you're starting your counter. But I'm going to do this one just like that. This is the third power series that needs to go in your memory. Because now you can do really cool things like if somebody asks you to do something with the inverse tangent of a half, like if you have to go evaluate the inverse tangent of a half and get some decimal place accuracy and no calculator because it's 1802 or whatever year you want it to be, I can just go throw halves into this polynomial instead. And I'm going to do 1/2 and 1/2 cubed over 3 and 1/2 fifth over 5, etc. Because polynomials are so much easier to deal with than inverse tangent, which you also hate. Okay, that was a lot. Let me know if you need anything. We're going to do 3 more power series tomorrow. Can't wait. See ya.